Welcome, we are PURA. Together with our 25 experienced friends, we are students at Hacettepe University. Our team consists of 3 departments: mechanical, electronic, and software. Our mechanical team comprises 13 members. We have designed a VTOL vehicle with dimensions of 12.47 feet by 5.90 feet. The electronic team consists of 5 members and is responsible for designing the electronic components and their communications in the project. Our software team consists of 6 members and is responsible for designing the vehicle's autopilot and image processing operations. The vehicle must be capable of flying a minimum of 15 miles in under 30 minutes to successfully accomplish its mission. Additionally, the vehicle must ensure precise delivery of payloads with an error margin of less than 20 feet as a secondary criterion for the mission. Taking into account these two critical criteria, it has been determined that the most suitable design for the mission is a VTOL design, and thus, our vehicle has been specifically engineered within the VTOL category. During the mission, it's crucial for the vehicle to stay within 25 feet of its planned route. To achieve this, we use here 3 plus RTK technology, which boosts our position accuracy from 8 feet down to just 0.08 feet. During the flight, the vehicle is required to identify and label human mannequins and papers from a height of 75 feet above the ground. To achieve this capability, a 12.3 megapixel high-quality camera paired with a 16mm telephoto adjustable lens has been employed. Moreover, to mitigate any noise caused by movement during the flight, a specially designed gimbal has been implemented. This gimbal effectively stabilizes the camera, ensuring that images are captured with the utmost clarity and detail, even in dynamic flight conditions. For object detection in captured images, the YOLO V6 model has been utilized, achieving an impressive MAP50 score of 0.92. To classify identified shapes within images, we utilize a custom-designed network developed by our team. This network boasts an impressive accuracy rate of 94%, enabling precise execution of the airdrop operation during missions. The airdrop system has been specially developed for the simultaneous transport of 5 other models to complete the mission in a single takeoff. To ensure seamless communication between the vehicle and the ground station throughout the mission area, it's imperative that the maximum distance between them doesn't exceed 0.85 miles. To maintain communication integrity, we chose the Power BM 5AC antenna, which has a range of more than 15 miles, and designed a specialized antenna tracking system for this mission. To meet mission requirements, we have integrated the Raspberry Pi 4 Model B and Pixar Orange Cube inside the vehicle. They communicate asynchronously via marbling protocols facilitated by MAV SDK. This setup ensures seamless task assignment to the autopilot system, enabling efficient and reliable task execution throughout the mission. To ensure our vehicle can navigate the mission environment safely and avoid collisions, it's essential for it to have obstacle avoidance capability. We achieve this by utilizing a Raspberry Pi HQ camera for image capture and processing the images with the graded search-based Bug2 algorithm. Each step in designing the vehicle has been carefully planned, resulting in a successful completion of the mission. You can see the list of requirements for the mission and the characteristics of the aircraft designed considering these requirements in the table. We designed the system in the most optimal configuration in the context of increasing the autonomous flight capabilities of the vehicle and achieving the power and propulsion system included the motor, ECS, battery, and considering the weight of the vehicle and acceleration requirements. We used the different brushless DC models of T motors for horizontal and vertical motors along with the respective ECSs. To extend the flight time, a 12S 40,000 mAh lithium-ion battery was used, resulting in a maximum flight time of 37 minutes. A Tarot 480 ampere power distribution board is used to safely distribute the high current and voltage from the battery to the motors. For the autopilot, we chose the Pixar Orange Cube for its high stability and control precision. Using it connected to the autopilot are a radio receiver, Raspberry Pi, 3DR 433 MHz telemetry, and here 3 GPS is also used. The ground control station operator communicates with the vehicle through telemetry via Q-Ground controller. The calibration and parameter settings of the vehicle were done by the avionics team. The pilot can intervene with the vehicle through the controller and receiver when necessary. For the mission, we facilitated that the transfer of the video obtained using a Raspberry Pi connected camera and bullet AC to the GCS operator. To minimize data loss, we developed a location-based antenna tracking system. The Power BM 5AC antenna used in the system creates an internet connection with the bullet AC router on the vehicle, enabling seamless transmission of video and data to the ground station over a wide area. When selecting the camera to be used for the ODLC mission, we paid attention to ensure that it would capture objects of standard A4 paper size. Therefore, we opted for the ArduCam 16-megapixel IMX519 model, prioritizing its resolution. With this choice, each image had a resolution of 5000 to 3000. At the determined flight altitude, the average resolution of standard objects became 50 to 50, which is quite sufficient for our recognition model. Additionally, we preferred to use a gimbal to ensure that the images could be captured smoothly. We decided to perform the image processing on the ground for high performance. For this purpose, we used a UAP AC M router
on the vehicle and power BM5 AC antenna connected to the ground station. We designed the ODLC in 3 stages: detection, classification, and localization. In the first stage, standard and emergency objects will be detected. If standard objects are detected, their locations will be cropped. In the second stage, the cropped standard objects will undergo pre-processing steps and will be classified based on their shape, letter, and color features. Finally, the coordinates of both types of objects will be calculated. For the detected stage, we tested various pre-trained recognition models. We created an extensive dataset for training using both physical and synthetic data. To generate synthetic data, we developed a dataset generator capable of placing at random angles, sizes, and orientations in all combinations. Subsequently, we labeled this dataset. We trained and tested different models, and we observed the highest performance with the YOLO V6 model. We designed an architecture for the classification stage. To achieve the high accuracy rate, we tested different preprocessing methods sequentially. As a result, we used scaling, masking, k-means, clustering, sharpening, and thresholding algorithms. These preprocessing steps enabled us to obtain more accurate and faster predictions. With our recognition model, we achieved an average map of 0.98 in 22 milliseconds on our custom generated dataset. For the classification model, we attained an accuracy rate of 0.93 in zero point 0.6 milliseconds. In the tests conducted so far, out of 75 objects, we successfully predicted all features of 64, while only mispredicting one feature for the remaining 11. During the localization stage, we computed the real-world coordinates of objects with known positions in the images using information such as instantaneous flight altitude, latitude, longitude, and camera focal length.
The payload mechanism is located on both sides of central region of its body. We designed the airdrop mechanism to be capable of carrying and safely releasing the designated payloads. The 5 servomotors used in the payload mechanism are connected to the Raspberry Pi and can be activated autonomously. The design has been made to utilize the volume in the fuselage in the most efficient way, and the overall structure of the payload mechanism has been designed in the form of the fuselage. The mission mechanism has a payload capacity of 5 units. The working logic of the mechanism works by suspending the payload from the vehicle with the rope. It has one pulley and servo system to release each load. The rope wound on the reel will slowly release the load to the target as the servo rotates. The covers of the mechanism are designed in a way not to spoil the body shape. The production was carried out with PLA filament using 3D printer for fast and easy production. The whole system weighs 2.2 liber, excluding the payload. The mechanism was tested in 2 different ways. These tests were conducted with the mission mechanism of the vehicle and in the air with the mission mechanism in the vehicle. 40 of each test were performed. The success rate of the test when the mechanism is not attached to the vehicle is 90%. The success rate of the test performed in the air with the mechanism in the vehicle is 85%. Due to the nature of the test setup, the payload reached the target with a high accuracy rate. It took approximately 15 seconds for the payload to reach the target. Although this mechanism is disadvantaged in terms of the load release time, it's very advantageous in terms of the high accuracy rate. The tests also showed that reloading took an average 5 minutes. In addition to this method, the method of parachute dropping the payload was also tried and tested. 30 tests were conducted with the parachute drop method, 20 of which failed due to the payload failing away from the target. When the parachute drop method is used, the payload falls in 5 seconds depending on the altitude. This method wasn't used due to the high failure rates in the tests. During the flight, various status such as altitude, speed, flight mode, and battery status are sent to the ground control station operator via TDR telemetry. Communication during the mission is facilitated through an internet network established via communication antenna tracking system. The Raspberry Pi is connected to the provider on board at the aircraft and receives video feed from the camera. Communication between the Raspberry Pi and the Pixel Cube is conducted by the Mavlink protocol. To achieve high antenna gain, an antenna tracking system synchronized with the ground station is utilized. This allows the antenna to be directed towards the aircraft in real time.
An internet communication network is established between the vehicle and the ground station using PB5AC Gen 2 antenna and bullet AC providers, which is chosen among other alternatives considered.
Through the TX channels of this network, data such as pressure, speed, altitude, flight mode, and images from the mission camera are transferred to the ground station, thereby increasing image processing speed on the ground. Commands for terminating the mission can be sent via RX channels. Trials have shown communication at certain distances achieving certain megapixel values. The Radiolink AT10 controller used by the pilot is connected to the vehicle Radiolink R12DS receiver, enabling the pilot to intervene manually when necessary. The vehicle has a wingspan of 149.6 inches and a body length of 70.9 inches. The diameter of propellers is 22 times 10 inch. The vertical motors are placed on the blades in the shape of the letter H. The shortest distance between these motors is 41.5 inches and the longest distance is 54.3 inches. The length is 70.9 inches. The body has been designed with soft lines to improve the aerodynamics and aesthetics of the vehicle. It's also designed with overhead wings to conserve volume and keep it the center of the gravity below the aerodynamic center. This increases the maneuverability of the vehicle. There are three hatches on the fuselage for easy access to the internal avionics. The body of the vehicle consists of three parts: nose, center body, and tail. The body parts are held together by specially designed connection parts and supports. Insert screws are placed on the parts in order to be able to assemble the supports and fittings with screws. Supports are designed and manufactured for secure attachment of the wings and stabilizers to the fuselage. The outer structure of the vehicle was produced by hand using glass fiber. The molds that will be used to shape the material are made of wood material, shaped and prepared using 5-axis CNC. PLA filament was used in the production of internal parts and supports, and the parts were produced on a 3D printer. The wingspan of the vehicle is 149 inches, and the longest chord is 14.6 inches, and the shortest chord is 9.8 inches. There are two flaps and two ailerons on the wings. The wingtips have wingtips to increase the efficiency of the lift generated by the wing. Wingtips are made of PLA filament and mounted on the wingtips. The wings of the vehicle consist of three sections and four parts. There are the center section, the right section, and the left section. The center section is 50 inches long, including the fuselage. The right and left sections are 40.2 inches long. The middle section is in two parts, and these parts are fixed to the fuselage. At the ends of the middle section, there are PLA parts that serve as connectors for fixing the arms holding the vertical motors. The arms holding the vertical motors are made of carbon and have length of 45.7 inches. In addition, the vertical motors are fixed on slots made of PLA filament. The left and right sections are mounted separately in this center area. Box toggle latches are used for mounting the wings. Plywood, wood, and carbon fiber pipes are used in the skeleton of the wing and stabilizer. The forces acting on the wing and vertical arms of the vehicle were subjected to the required laws within the ACES program. When data obtained from the analysis were examined, it was seen that the materials used in the vertical arms and wings were within the elastic limits. Tests were carried out on the vehicle to prove durability and ensure flight safety. The forces falling on the wing were calculated. The weights corresponding to these calculated forces were evenly distributed on the wing, and the flexure and strength of the wing were tested. When selecting a wing profile, the primary parameter considered was enhancing the aerodynamic performance of the UF. For this purpose, a 2D profile analysis was conducted using the XFLR5 program. During the analysis, lift, drag, and pitching moments coefficients were compared, using air properties at 15 degrees. Reynolds number and Mach number were calculated using the data in the table on the left. It was observed that the calculated Reynolds number indicates a flow closer to turbulent, with the laminar and turbulent flow coexisting. The N10 airfoil profile was chosen because the analysis resulted in a higher CL and lower CD values when compared with the multiple profiles. The thrust required for various angles of attack was interpreted from the alpha graph. It was observed that the vehicle operates efficiently at around 5 degrees of mounting angle. Examining the alpha graph, the ability of the wing to generate lift at 0 degrees and the relatively high stall angle stand out to prominent features. This suggests that the wing can produce effective lift even at low angles of attack. Pixar Orange Cube has been selected as the autopilot control unit of our vehicle. It provides precision in the transition of our vehicle from vertical to horizontal mode, making the transition smoother. In addition, it has a high-performance H7 processor, offers a performance and stable solution for PX4-powered flight. It is the most up-to-date and powerful model in the Cube Pilot ecosystem. It also has a temperature and vibration-resistant IMU has enabled the vehicle to perform mission more effectively and more accurately. In order to precisely determine the position of our vehicle, we use the GPS 3 Plus, which has a high-accuracy GNSS module that can determine the position of the vehicle up to 8 feet. By integrating RTK with the GPS 3 Plus, the position accuracy was reduced from 8 feet to 0.08 feet, allowing the vehicle to pass through waypoints accurately. Reducing our error rate, increase the airdrop hit rate, and reduce the waypoint error, allowing us to perform mission in the best way. We made various parametric changes in the graphics to ensure consistency between the set point and estimated values. This helped making the flight more balanced and stable. Additionally, we limited the vehicle's maneuver angles and responses to commands in order to prevent sudden maneuver disturbances. After the vehicle was finalized, a total of 13 flights were carried out over a period of 1 month. These flights started as fully manually at the beginning, and over time, different flights were tried to be fully autonomous. The results of these flights are shown in the table.
Our vehicle managed to pass through almost all waypoints and follow the computed route as long as the waypoints were not too close to each other. The experiments conducted in the flight for about 1 month are as shown in the tables. We chose the Raspberry Pi HQ camera model for the obstacle avoidance task due to its large sensor size, which enables capturing large objects. For the computer, we opted for the Raspberry Pi 4 because of its lightweight design and compatibility with the camera. Firstly, we processed images from the camera using computer to detect if there were any obstacles ahead. To avoid the object, we utilized BAG2 algorithm based on greedy search. This algorithm enables the vehicle to detect obstacles in front of it. Prompting it to make a turn and then navigate around the obstacle. If it cannot avoid the obstacle, it will turn to try an alternative route. This ensures that the vehicle avoids collisions and progresses safely. We created a dataset consisting of image captured from our own drone and aircraft to train our model. We aim to enhance this dataset by augmenting it with open source data to achieve high accuracy rates. Subsequently, we conducted training using the fast and highly accurate YOLO V6 model. This enabled us to successfully perform real-time evasion maneuvers. The advantages provided by different approaches in VTOL vehicle designs are critical. Factors such as vertical takeoff landing, operation in confined spaces, and rapid mission completion enhance VTOL's efficiency and offer a flexible flight experience. Considering the competition conditions, in order to fly a distance of 25 miles in 30 minutes, the average speed of the designed vehicle should be approximately 50 feet per second. Rotary wing UAVs need to fly at an angle of 20 degrees to reach these speeds. Flying the vehicle at such a high inclination poses at a great risk and reduces efficiency. During flight, VTOL vehicles have been observed to provide longer flight times compared to drones because they generate lift from their wings. Finally, in factors such as average flight speed, maneuverability, and payload, our VTOL vehicle has more advantages according to the analysis results of our two different designs. Especially, according to the experiences we have gained from our fixed-wing vehicles in our past years, it is much more difficult to accurately drop the payload on the target than VTOL vehicles. The biggest advantages of VTOL compared to the fixed wings is the high accuracy. However, since we are making a VTOL vehicle, we didn't have a problem with the airfield requirement of 85 feet. We implemented various measures and procedures to minimize risks during production and testing stages. During production, we used masks, gloves, and protective goggles to prevent chemical harm to the human body from the materials used. We followed the usage procedures of the mechanical tools. Due to working with high currents and voltages, we regularly checked the batteries and charged them in isolated area. In the testing stage, since the propeller size used in the vehicle were quite large, we installed the propellers last after the entire system was set up and checked if they were securely attached to minimize the possibility of motor movement due to signal leakage. We chose a testing area away from residential areas and crowds to prevent injuries and property damage in a case of fall. Finally, in a case of communication loss between safety pilot and vehicle, autopilot activates failsafe and returns home in drone mode. We conducted various experiments to integrate our image processing algorithm with the airdrop mechanism. We can detect shapes and humans with a 98 MAPE 50 score and classify shapes with a 93 accuracy score. Our airdrop mechanism operates with an approximate 85 success rate during missions. We can maintain uninterrupted communication between our vehicle and mission area using the PURA BM5 AC antenna. Using the combination of GPS tree and RTK, we can navigate through all waypoints as long as they are not too close to each other. The table shows results from different flights. We experimented with different algorithms for obstacle avoidance and concluded that YOLO V6 is the algorithm that allows us to perform this task quickly and accurately. In every test we conducted, our algorithm successfully avoided every object it detected. Among the total of 13 flights we conducted, the 5th, 11th, and 12th flights were specifically designed to simulate the mission entirely. During these flights, manual takeoff and landing were performed, while fully autonomous flight was executed in between. In all three flights, all objects were correctly detected, and 4 out of our payloads reached the target within a radius of less than 15 feet. Here is a manual flight showing takeoff, getting 1000 feet from safety pilot and landing. In this flight, our aircraft autonomously progressed up to approximately 200 feet, at which point our safety pilot switches the vehicle to the manual mode, taking control and landing the aircraft back at the takeoff point. Here's our 5th flight statistics. Our setup time is 12 minutes, mission time is 22 minutes, and teardown time is 7 minutes. Here's the video of our 5th flight. Throughout the video, we have detailedly showed how our team designed our vehicle by taking into account the requirements of the task. We have shown the various stages of designing our vehicle. We ensured the adequacy for the task with repeated real-time simulations. Thank you for watching. See you in the field. always forward for the best.